In my experience, people don't write libraries unprompted. They don't wake up one morning and decide, I'm going to write a library to solve a problem I've never encountered with which I have no experience. No, a library is born from a problem. It's born from exploration of that problem. It's born from lessons learned thereby. And so I don't want to just talk to you about the Platonic idea of modern C++ library design today. No, instead I want to introduce you to a problem domain I experienced, guide you through it, and show you how modern C++ library design was able to solve and address every single one. But this means nothing if we don't have a problem, so let's get started by introducing that. On the screen is the ticker symbol of an instrument traded on a financial exchange. Our problem is to query relevant data about such a symbol on a time range or otherwise. And the way we're going to accomplish this is start out by, of course, building a proprietary time series database. Fortunately, me and my team have already done that because it would not fit in a 90-minute talk. After that, we need to go out and find some interesting market data and put it in that database. And once again, fortunately, my team and I have already done that. Which brings us to the actual problem. Which brings us to querying that time series database and getting out the information that we're interested in. But this formulation means nothing if you don't know what a time series database is. It means nothing if you don't know what a time series is. So let's start with an introduction to that. A time series is a sequence of data whose most significant key is a temporal one, ordered physically in time. A time series everyone's probably familiar with is a log. Sure, log messages have other pieces of information we're interested in, like an emitting component and a level, but the most important key, the one they're physically laid out based on, is their temporal key, is the timestamp. The proprietary time series database my team and I have built is optimized for financial applications. It's a file-based database, so the first step of a query is identifying a file you're going to query from, which necessarily limits the number of time series to which you're exposed. Then, within each file, we provide a theoretically unbounded number of keys. Not really theoretically unbounded, but a 24-byte space. I doubt you're going to fill that. So inside of a file, you can query the constituent time series equally efficiently as each other. There's a seemingly infinite number of them in there. But perhaps most interestingly, this time series database, despite being built to handle the immense volumes of market data that are broadcast by financial exchanges, supports live intraday querying. As data is ingested into the database, you can query it immediately. Not just query it immediately, but query it immediately with the same interface with which you would interact with historical data. We interact with data equally whether it occurred a second ago, a minute ago, an hour ago, a week ago, or a year ago. So understanding that, let's take a look at some of the code artifacts the core database engine gives us that we're going to use to build our solution. First, we need to understand how it actually lays out and stores data, and it stores data as a sequence of bytes with this header. We can see that since it's a time series database, featuring prominently in this erased update header, erased because it doesn't have a type corresponding to the buffer of bytes, there's an 8-byte timestamp, 64 bits, the number of nanoseconds that have elapsed since Unix epoch. Also, we need to know how many bytes come after this, so we assign 24 bits to represent that, and then we surrender the remaining 8 bits to our user to use for whatever they want. Most users use this as some kind of discriminant so they can describe in their application domain what data follows in the free-form buffer of bytes that occur after this header. I said earlier there was a key, a 24-byte key, and so we have a structure for that has a 24-byte buffer of chars in it. Don't let the type deceive you. This is a free-form buffer of bytes. There's no requirement that it be null-terminated, contain ASCII characters, or be otherwise human-readable. You get the full 24-byte key space. Which brings us to our interactions with the database engine as we pull results out of it. Which brings us to how the database communicates to us the result of an ongoing query, which brings us to the update status enumeration, with 3 enumerators. The purpose of 2 of them is probably immediately obvious: complete and processed. Complete is returned to you when you've explored the entire time range you're querying. Say you're querying between 2 and 4 p.m. and you've gotten every single update back on that time range, of course then complete is returned. And if there's another update available for you to consume, processed is returned. This much was obvious. Which leaves the heterodox enumerator in that enumeration, which leaves none for now. And that brings us back to the fact that this time series database engine supports live intraday querying. Just because you can form a query between 2 and 4 p.m. doesn't mean 4 p.m. has happened yet. On the ingesting side, we may only be up to 3 p.m. And in that case, when our query catches up to live market data, it will be inappropriate to return complete. That would give a false impression to our user. We would tell them they've seen all of the updates between 2 and 4 p.m., but that would be a lie. Another alternative, of course, would be to consume the thread to block it until we can yield an update or complete, but this is also unworkable. We're going to be in a server. We're going to want to use those threads for different things, for different queries. We're going to want to multiplex them. Just taking ownership of one because your query caught up to live market data would be grossly inappropriate. And not only this, our deployment experience indicates this is not even the behavior that consumers want. They want an incomplete data set with a trailing indication that it's incomplete so they can just come back and try again later. And so in these situations, we return none for now to communicate the fact that while there's no data available at present, you can, if you want, wait, come back later, and hope to get more data. But this is just an enumeration. How do we actually interact with the database engine and pull data out of it? The way we do that is with the open query class, which has 3 data members, the begin and end of the time range, and that symbol key we're querying on within the file we're querying. Then it has a trinary constructor, which just populates those members, and a nullary invocable run function, which returns an outcome result over that update status enumeration. An outcome result can be either errored or have a value, and so if the database encounters a problem, we just get back an errored outcome result. There's nothing in it. We can inspect it to determine qualities of the error, but we don't reveal any enumerator to our caller. If, on the other hand, advancing the query succeeds, we return an update status enumerator, and that indicates to our caller how they should proceed. If it's processed, they can go and invoke the nullary invocable last update member function and get back a pointer to the next update in the sequence. We return a pointer, not something value semantic, because we want to reserve to ourselves the right to optimize memory allocation, to reuse pages, to use memory map file techniques. But armed with this class, we can actually query the database. If all the data for a certain symbol is in a single time series, we can just pull it all out. And isn't that what we originally set out to do? But as we think about market data and its use cases, we realize that we transmit a variety of information about symbols. There are trades, there are orders, there are statuses, there are statistics, and nothing says that every user wants all of those merged together in one monstrous stream. Some users may just want trades, some just statuses, and others some combination of the two. But there are still going to be users who want all of them. And so if we go into the database engine and we decide to shard these out into separate time series with separate keys or in separate files, we need some way to recombine them. We can't just address the entire problem space with a single open query, because what we've discovered about our problem domain is that interesting logical queries consist of queries against multiple symbols in multiple files across perhaps multiple time ranges. And when we perform such queries, we want to yield results back to our users with that fundamental property of a time series that all of the updates are delivered in temporal sequence. And so what we need is streaming merge sort. When we're presented with 2 time series like this, we need to look at them and repeatedly take the one with the lowest valued timestamp. We need to take first this trade and then this order. At some point, these time series will become exhausted, in which case you just fall back to the scenario where you have one time series and you can just repeatedly take the next result from it. And so we go off and we write some code to do this. We write something called merge sort. We can push back open queries into it by reference. After all, the responsibility of this class is not to manage the lifetime of queries, it's just to merge sort them. And then we can run it kind of in the same way we run queries. We get back a struct that contains an update status and a pointer. And if that update status is processed, we can chase that pointer and we find a query. We can chase the pointer returned by its last update member function, and we find the next update in the sequence. Which doesn't really seem like a problem in our problem domain. We just had to write a class that behind the scenes repeatedly pops things off a heap and pushes things back into it. But then we set out to actually write this code. We try and implement this class, or we just think a little bit longer about the problem. And then we remember something. We remember that we wrote a live intraday time series database, one which can return none for now when it catches up to live market data. And so what do we do in this situation? What do we do when we have updates on the right-hand time series, but the left-hand time series just says none for now? What does that none for now mean? Does it mean that all the data up to the current wall clock time has been ingested and reported? Can we release all the updates on the right-hand side whose timestamp is numerically lower than the current time? Or does that none for now on the left-hand side indicate that the left-hand side has fallen behind? If we go ahead and release updates on the right-hand side, will we later find updates on the left-hand side that have doomed us to release data out of order, to violate that time series guarantee we want to maintain? And some people might think this problem isn't even worth solving. A lot of data flows from market data exchanges. I will just wait for the next update. But then we think back to why we originally set out to do this. I said that you could shard market data out, trades, orders, statuses, statistics, levels. And there's a lot of trades for a lot of symbols. There are some symbols, in fact, that you will find trading multiple times each and every second. But at the same time, you can also find examples of market data symbols that change status twice a day, when they open at 9:30 and when they close at 4:30. Did we really write this interesting high-performance live intraday querying time series database just so we could sit around and yield no trades from 9:30 until 4:30 because we're waiting for the next status update? No, what we've discovered in the awkwardness of this situation is the fact that we coupled two things that were unrelated when we formulated our open query interface. We married the delivery of bona fide pieces of data to the delivery of information about the passage of time. And we need to decouple those things by going back to open query and adding a new member variable, most recent known timestamp, which, when run returns none for now, will be updated to communicate to us the most recent timestamp about which data has been ingested, independent of the arrival of any bona fide data. The ingesting side may know this because it received data about another symbol, but we also provide the possibility for the ingesting side to tell the file it's outputting that time has passed, independent of the arrival of any data whatsoever. And so now that we've done this, when we go back to merge sorting, we discover that on the left-hand side, none for now has been enriched with a timestamp. It's been enriched with information about the most recent known timestamp, and so we can go back to merge sorting the way we were before. We can just take from the right-hand side all of the updates with a lower value timestamp and only wait when it's actually appropriate for us to do so. Sit there calling run on the left-hand side query until none for now bumps its timestamp and we can go back to releasing updates. But this isn't the most interesting thing that falls out of the idea that we have schematically distinct data. What we're now encountering is the fact that we have update heterogeneity. We have an erased update header and then a free-form buffer of bytes, and we're talking about those buffers of bytes as though they have some semantic meaning. And in order to layer semantic meaning on top of them, we have to go out and do unsafe operations. We have to copy around bytes, we have to start lifetimes, we have to trust that our user does each and every one of those things correctly every single time. And the odds of them avoiding all that undefined behavior consistently is practically zero. And so what we need is additional functionality. We need a new operation that helps to layer some safety on top of this ecosystem. We need update as, which accepts that raw erased update header and layers type safety on top by internalizing the checks necessary for safety, by internalizing those tricky to get right operations in C++ that can bring into being a rich, strongly typed object in that storage. Only if that operation succeeds do we return a successful result containing an appropriately typed pointer. If it fails, we return an errored result. That unsafe pointer never escapes, and the user gets a descriptive error message about what went wrong. And this operation is interesting. The primitives built out of are interesting. The techniques to implement it are interesting, so much so that I gave an entire hour-long talk about it. So if you want to know more about it's implemented, go and watch that. For now, we're going to take and use it and integrate it into our querying system. We're going to add update as query, which yields strongly typed updates that our users can consume without sharp edges. In doing this, of course, we've taken our update heterogeneity and lifted it to the level of query heterogeneity. And thinking back to our merge sorter, it only accepts open queries, so we have to go back and rearrange it, make it templated, make it able to accept a variant of heterogeneous queries. But that's not what's happened on this slide that's interesting. That's not even worth reviewing. What's happened that's interesting on this slide is that we've discovered that there was something lurking behind OpenQuery beyond its static and particular type. Because this class looks a lot like OpenQuery. It has a nullary invocable run function, which returns an outcome result of an update status. It has a nullary invocable last update, which returns something pointer-like. But it's pointer-like. It's a different type. It's not a pointer to an erased update. So we haven't discovered any kind of runtime polymorphism here. What we've discovered lurking behind OpenQuery is a concept. What we've discovered is that it wasn't particularly OpenQuery we cared about. We only cared about the operations we could perform on it, that we could run it, and that we could call last update and get back something pointer-like. But something more concerning has happened here too, because we lost something in this transformation. Before I had an OpenQuery, I called run on it, I got back a raw erased update header. It was unsafe to be sure, but I had the update as basis operation. I could call it, I could get back a safe pointer, I could layer that on outside, and if update as failed, I still had access to the raw erased update. I still had access to those raw bytes. I could take and I could synthesize a rich error message full of context and show it to my users. But now I've taken both those things and hidden them behind the run member function in this class. When the conversion fails, it just fails. It has no way to publish that information out to me because it can't possibly do it through last update because last update is strongly typed, and the last thing I want to do is use reinterpret cast to break the type system. And some people might be inclined to say this doesn't really matter, right? This loss of context is the price I'm willing to pay for abstraction and safety. If I get error messages that are very slightly worse by making things more convenient for my users, I will happily pay that price. But I disagree with that sentiment so strongly that I gave an entire hour-long talk about it. And so we're going to have to do something better. We're going to have to extend the basis operations of update as query so it can expose that raw context to us. We go back and we give it a new member function, nullary invocable, which just returns the erased update, which we can call if the conversion fails, and we can still emit those error messages. But this isn't the win that we think it is. Because just a moment ago, we were talking about how wonderful it was that OpenQuery and update as query could be used identically. They both satisfied the same concept. And then in the next sentence, I turned around and said, well, you know, update as query's interface isn't really so great. We need to add another member function to it. And maybe we could approach this problem by going back to OpenQuery and extending it with raw last update. But why would we do that? OpenQuery doesn't do this. It doesn't need to know about this name. It doesn't need to know about this functionality. It's just baked into the last update. Why would we go and litter its API with member functions that don't appertain to its core function? And so what we need is to reach for something called a customizable function, something that implements a different protocol, because after all, we don't want to go out and write a generic error handling routine and inside of it degenericize it by making it check properties of its argument and branch based on those. No, instead we want to separate those concerns out. We want to write an overload set that deals with this. Raw last update constrained for the raw last update protocol returns raw last update. But if the raw last update protocol doesn't apply, we can just provide an unconstrained overload that just returns last update. Now we can interact with OpenQuery and update as query equally using this function. We don't need to litter OpenQuery's API with functions that don't appertain to its core use case, and we still get the richness that update as query can morally report. And most importantly, in getting our cake and eating it too, when we write that error handling routine, we have a consistent way to interact with all queries, to extract all the context and richness from them, regardless of what their actual core function is. But we spent quite a bit of time talking to this point about queries that are run, which raises the question of run by who and under what circumstances and with what expectations. Because I mentioned that we're running in a servo ecosystem, we're probably sharing and multiplexing threads. And how is that accomplished? And that person who provides context for us to run, who surrenders the CPU to us by calling us, what kind of guarantees do they expect? This is the problem of incremental computation. Because if they're going to actually share the CPU fairly and not let other queries get starved, they need to have some guarantee that we return to them in a bounded amount of time. And both halves of this question are very interesting, both the person calling us and multiplexing the thread and us being called providing this guarantee. But our caller situation is so interesting that I gave an entire hour-long talk about it. And so we're just going to assume that they're calling us and think about how we can return the CPU in a bounded amount of time. But then we take a step back and we survey our ecosystem. We think about OpenQuery and we realize, wait, OpenQuery run already does exactly this. We call it, it advances to the next update and returns to us immediately. Update as query enriches this, to be sure, but only by adding a bounded amount of work, one attempt at converting the yielded update. And so maybe we just have this property already. Maybe we don't need to do anything, we just need to discuss it, think about it, and rest assured that our ecosystem represents this property. But there's a problem here. I've heard it said that in software engineering, 2 is an impossible number. You have 0 of something, 1 of it, or an infinite number. When you all walked into this room, you didn't know about any queries. There were 0 of them. Then I showed you OpenQuery early on, and there was 1 query. Then moments ago, we discovered update as query, and now we have 2, which means we have an unbounded number of queries modeling an unbounded number of behaviors. We have to take our search beyond OpenQuery and update as query and think about what other behaviors we might want to add to this ecosystem and how well they play or don't with this guarantee. And one thing we may want to enrich our ecosystem with is filtering. We may want to remove results from the output stream that we can't remove by using the core database functions alone. So what happens then? Well, filtering is something that C++ developers are comfortable with. We do it all the time. If I take this vector of 7 integers and I give you a predicate and I use some range as magic to filter it, everyone in this room is probably looking at the slide saying, yeah, that just outputs 6, 5, 5, 6. There's nothing really interesting here. But let's go deeper. Let's think about what's happening at each step of this example. When we go to that filtering view and we get the begin iterator, it points at the first element which satisfies the predicate. So we dereference it, we process it somehow, and we move on with our lives. And the way you move on with your life in the ranges ecosystem is you increment the iterator, which means the iterator points at the first element, or the element at the first index, which also satisfies the predicate, and so we can just return and let our user process that in turn. But then we get incremented again. And the element we end up pointing at does not satisfy the predicate. And so we need to increment the iterator again, and again, and again. And what we're discovering is that for arbitrary inputs and arbitrary predicates, we don't have that guarantee for filtering. The reason why is because the iterator model marries the step operation, the performance of some work, with iterator validity or it comparing equal to the sentinel. We have no way to say to our caller, I'm giving you the CPU back because I'm trying to be nice, but please do not dereference this iterator. It just doesn't work in the model. And OpenQuery has exactly the same problem. Because when run returns processed, we guarantee that you can call last update and chase that pointer. So what we need to do is we need to amend our ecosystem again. We've discovered a new problem that we need to address by changing what we're doing. We need to allow last update to return null putter, but now our old friend none for now comes back, that sorting problem. How do I sort null putter relative to the richness of an update with a timestamp? I can't do it. I need some way to get temporal information separately from bona fide results that should be included in the output set. So we add a new operation to our hypothetical filtering query called last position, which always returns something we can use for sorting, which yields a sort key even if last update yields nothing. But now we face exactly the same problem we faced with raw last update. We've made our interface to our queries inconsistent. We can't sort them generically anymore, and so we need to go out and we need to write a new free function to implement that protocol too. Which brings us to the last problem I want to talk about with this ecosystem before we move on. And that's that right now we can create a merge sort and we can push some queries into it and we can run it and we can get data out, but that is not how market data actually works. Market data exchanges transmit market data on many channels in parallel. We want to receive it in parallel, process it in parallel, and write it in parallel. And that means the first step of our query isn't just going off and grabbing some market data. We need to open a manifest of all the channels we've seen for that day and query that. And each time we become aware of a channel, we need to then query its symbol manifest to see if the symbol we're looking for is on that channel. And if it is, only then can we go and open those market data queries. Because our actual queries are hierarchical. We need them to dynamically expand. And I took 2 stabs at modeling this problem, and neither of them worked to my satisfaction. The first one was to embed that logic in a query, which would create queries and then add them back to its own merge sorter, which not only introduced the problem of the query managing lifetimes, but it was also self-referential and made lifetimes in general difficult to reason about. And the whole point I'm exploring this problem domain and trying to model this ecosystem is to make things easier for my user, not harder. And so the solution that ended up getting deployed was a strict enforcement of a fixed cardinality hierarchy. The classes that directly model it, but which don't really release enough context to you and aren't rich enough to be extended, as we'll discover later. Because what I was discovering in this exploration is that walking through this problem domain, the productive thing I was producing wasn't code that I was delivering to my client, even though I was writing code and I was delivering it to my client. The actual valuable part of this endeavor was the lessons I was learning about the problem domain as I went. And at some point, I needed to recognize that that was the value I'd taken from this exercise, and that the code I'd written as a consequence of that investigation was not worth iterating on further. I needed to do something that software engineers are often taught about in school, but which they rarely do in their day-to-day lives. I needed to decide that now was the time to throw away the throwaway prototype and replace it with something new, which actually modeled my now full understanding of the problem domain. But that raises the question of, what new model are we talking about? The new model we're talking about is one of streams, which yield results by performing work incrementally. And each of those increments, each of those results they yield, we can divide into one of four categories. They can either be an error indicating that forward progress could not be made, or a result indicating that's some interesting data that should actually be included in the result set. But maybe they can't do that, and so they return something we call a position, which just indicates that some work was done. We arrived somewhere in the sequence of results that will be yielded by the stream, but we didn't generate anything that qualifies for inclusion in the final output. We can subdivide this into two categories. One is just us yielding the CPU to be nice. That's the consequence of our filtering problem. And the other is us giving control of the CPU back because we're actually incapable of yielding a result right now due to something related to the passage of time. Our caller shouldn't try and call us again immediately and expect a different result. But this is just a platonic description of a model. How do we actually model this taxonomy of results in C++ code? What type can we actually use to represent it? And the type we're going to use is an outcome result of a stood variant of some alternatives. The outcome result there stores the error. The stream encounters an error, that first entry in our categories. We get back an error result, there's no variant, and we can go off and handle that appropriately. But if we succeed, if we yield something that is a result, a position, or a completion, we get a variant with some alternative in it. But this just kicks the can down the road. How can we layer this three-way categorization on top of the free-form alternatives of a variant? And the way we're going to do that is we're going to actually write some C++ code. We're going to write an enumeration of the three remaining categories. Enumerators are result, position, and completion. And then we're going to write a template variable which associates types with a category. There are many customization techniques you can use in C++. The reason I've chosen this one is because I want the category of a type to be a function of the type only. No runtime properties influence the categorization of a type, and so I embed that information in an association with the type. I default this to result because overwhelmingly that's what you want, and that saves you from interacting with specializing this in the vast majority of cases. So now that we can form that association, let's of course write a concept to check it. A binary concept that checks to see if some type T is a member of some category. Note that because of the context in which concepts are used, we apply stood remove CV ref of T, because often in the way you write concept usage and requires expressions, the things you're passing in are ref or CV qualified, and you don't actually care about that. So we strip it off to save our users from writing a lot of boilerplate. With this binary concept, we can just go ahead and write three unary concepts, which check each and every one of the categories we're interested in. But this in turn is us just kicking the can down the road further. We now understand our taxonomy. We understand how it's modeled in C++ code, but the entire model was predicated on something called a stream, and we have no idea what that is. It was predicated on the idea that we could step that stream to get these results, but we have no idea how to do that. And so in modeling this solution, I'm going to lean into the principles of C++ generic programming. I'm going to define just operations and not worry about types. I'm going to whip out something that looks like it belongs in a standards paper, and I'm going to say that a sub-expression S denotes a stream if the expression run of S is well formed. And we can immediately turn around and reify this in C++ code, which checks it. We can just go ahead and write a concept. Note that in this concept, I forward T through because on the preceding slide, I said a sub-expression S. I didn't say an L value S. I didn't say an R value S, I said a sub-expression S, and sub-expressions have value category, and the onus is on us to propagate it. Something may be a stream when it's an R value, but not when it's an L value. And it's not up to us to pass judgment on our users for doing that. We just model it and leave them to their own devices. But this just raises more questions. If we can call run with something, then it's a stream, but how is run defined? What does run do? And to help me specify this, I actually enlisted the help of a C++ library wording expert. We wrote a formal specification that is of the quality that could go in the C++ standard for that, and I'm going to show it to you, and then turn around and write code which actually implements it, because that kind of wording is widely regarded as being arcane, difficult to understand, and opaque. And so I'm going to say that the name run denotes a customization point object. The first thing we learn from this is that run is not a function. Our users can't use ADL to call run. It and all its sharp edges are completely swept off the table. Then we're going to define something that is a helper for us in ongoing specification, that just makes it easier for us to talk about something. And I can tell this is a helper and not something we're actually exposing to our users because it's in italics and rendered in kebab case. So this is not part of our API service. It's just something that helps us talk about functionality going forward. We say let doRunOfS evaluate the expression. And when we say that, what we mean is that there's no difference between doRunOfS and the expression it's actually defined in terms of. If you can detect the difference, it's probably a bug. The first bullet point says that doRunOfS could evaluate the expression s.run if that expression is well-formed and yields an object type. An object type in C++ is any type that's not void, that's not a reference, and is not a function type. So if both of those apply, then doRunOfS just means do s.run. But we know that's not going to be valid in all cases, and so we fall down to that second bullet point. We say that as a fallback, doRunOfS might be a shorthand for runOfS if that expression is well-formed and yields an object type where the meaning of run is established as if by performing argument-dependent lookup only. And so on the same slide that I took ADL off the table for my users interacting with me, I put the responsibility on me to use ADL to interoperate with people who are implementing streams. Now, of course, if neither of these protocols apply, doRunOfS is ill-formed. But not ill-formed in any loosey-goosey way, ill-formed in a very specific way. Ill-formed in a way that you could detect with Safini, that you could detect with a requires expression, because doRunOfS and everything we're going to build is going to be a good citizen in the generic programming ecosystem. But that's just the specification. It's opaque and hard to read and reason about. How can we actually model that in C++ code we can put into a compiler and actually use? And the way we're going to start doing that is open a detail namespace, but not just a detail namespace, also a sub-namespace of our detail namespace named after our component. This way we get a truly blank slate. We don't have to worry about other headers we write defining detail functionality that collides with us. And then the first thing we put in that detail namespace is the declaration, but not definition, of a function named run, which takes no arguments. And what this means is that within this namespace, when you call a function called run, you're going to cause regular unqualified name lookup to occur. It's going to propagate outwards looking for a name called run, and it's going to find this one and stop its outward search. Because it finds a function, it's going to know it needs to do ADL later, and it's going to stop its outward search because it found a match. So we start with a candidate set that just contains this function. And then we go and perform ADL, we populate the remainder of our candidate set, we need to do overload resolution. But as we think back to the preceding slide, to the member function, to the free function protocol which used ADL, we were unary invoking, not nullary invoking that function. Which means that despite the fact this poison pill stops regular unqualified name lookup from propagating outwards, it's never a candidate to be called. Which means that within this namespace, when we call run unqualified, the meaning of the name run is established as if by argument-dependent lookup only. And so with one declaration, we've already implemented one of the things we specified on the preceding slide. But now we have a cascading list of a priority to implement. And so let's write some concepts. Let's write one that checks to see if the result returned by one of our protocols qualifies. If it's an object type, it just evaluates a type trait. Now we need to check to see if that first entry in our bulleted list, the member protocol, applies. And so we write a concept that checks that. Note that I'm careful again to forward things through because on the preceding slide, I wasn't talking about L values or R values. I was talking about expressions with a value category which we're obligated to preserve. Of course, once we're done with the actual expression, we're sure to check its return type because we had 2 requirements for this protocol, not 1. Of course, this isn't the end of things. We had 2 bullets on the preceding slide, and so we define a new concept which checks the free function protocol. Since this only springs into action if the member protocol doesn't apply, we start by negating that concept and then combine it with a requires expression, which looks very similar to the one above, which actually performs that unqualified name lookup we discussed at some length earlier. Other than that, it's mostly the same. Now, to help us going forward, we're going to define a helper concept that just checks to see if do run generally applies with either of the protocols we specified. Which leaves me actually writing the code that implements do run. And so we add an overload that is constrained on the member protocol and just performs that. But notice that I'm very careful to aggressively annotate this with constexpr and appropriate no except. And the reason I'm doing that is because our specification talks in terms of expressions and evaluating them. And if 2 things are expression equivalent, surely if one of them is no except, then the other one is too, right? If one of them is a constant expression, then the other one must be as well. With this overload added, all we need to do is add an overload that implements our free function protocol, and we finally implemented our do run helper. Which leaves one glaring question. Why are we using ADL? ADL is something that is fraught with all kinds of danger, and very smart people have spent a lot of time trying to tame it. But then recently the community seems to think the winds are blowing the other way and has said, well, we just don't want to use ADL at all. And the reason I'm using ADL is because to me, ADL gives me the generic equivalent of the open-closed principle. I want people participant in my ecosystem to have classes which are open for extension and closed for modification. If someone somewhere writes something that morally models a stream but doesn't obey my protocol, I don't want them to have to modify their class in order to be a first-class participant in my ecosystem. I just want them to open their containing namespace, write an appropriate unary invocable run free function, and suddenly they are a first-class participant in the ecosystem I'm writing. Maybe these use cases don't apply to you. Maybe you're not persuaded by them. No one says you need to use ADL to write a modern C++ library. I've just chosen to do so and figured I would show you how. Which puts me in the awkward position of putting on the screen the most grotesque slide in the entire talk, which is where I actually specify what it is that run does in terms of do run. I don't think people in this room will be enriched by me reading every single word on this slide, and so I'm going to leave it here for you to read through while I talk about what we're trying to accomplish here. We want to give callers of run a consistent interface. Earlier we said we use an outcome result of a stood variant of one or more alternatives. We want to guarantee that when you call run and it's well-formed, that is exactly what you get. But at the same time, if you're implementing a stream, I don't want you to have to litter your interface with decorations that don't appertain to you. If your stream's run function never fails, why should it return something wrapped by an outcome result? If it only returns one type of thing, why should it return a variant? And so what all these bullets on the slide do is lay out the protocol for rewrapping any type returned to me into one which is acceptable to be returned by the run customization point object. And that's interesting on its own, but I want to draw your attention to the first bullet point. The first bullet point says that in the happy case, in the case where the person implementing the stream returns exactly the type we expect, then the run customization point object is expression equivalent to E, which is in turn expression equivalent to do run of S. And what we're saying in all of this intense language is we're saying that if the implementer of the stream returns something of the form that we expect, then because we're expression equivalent to the do run protocol thereon, we are banned by this specification from adding any operations whatsoever outside of that. It must be exactly as if the user had typed the appropriate do run protocol in their code. This is something that will become important in just a moment. In all of the other cases, we give ourselves leeway to do additional operations to achieve the rewrapping. And if that can't be performed, then at the end of the slide, the entire customization point object is ill-formed. Once again, ill-formed in a way that can be detected with Safini or requires expressions. So let's jump into the implementation. Let's figure out how we can actually write something that implements this specification. Let's start by reopening that detail namespace and starting to write an overload set for something called wrap, which will achieve the rewrapping of things returned by the do run protocol. And the first entry in this overload set is one which matches when we get back exactly what we expect. We get back an outcome result of a stood variant of some alternatives. But then I go and I just delete it. It's ill-formed to call it in this way. And the reason for that is because if it was well-formed to call, and we called it with the result of do_run would return a PR value. We would need to materialize that PR value in order to bind it to that R value reference, and then if we wanted to return it out, we would have to move it. But nowhere in the happy case on the preceding slides did the specification give us permission to move anything. We need to pass PR values through unmaterialized. We cannot use this implementation strategy in that case. We need to figure out something else, and so we delete it. But as I pointed out in the preceding slides, we give ourselves leeway in all of the other cases, so we can add overloads for those. We can add an overload that takes in a stood variant and stuffs it in an outcome result of that stood variant. We can write an overload which accepts an outcome result of a type that isn't a variant and which returns an errored outcome result if that's falsy, if it represents an error, and otherwise just plums that result through into a stood variant of one alternative in an outcome result. And then, of course, we can write an overload that takes just a T and wraps it appropriately in both an outcome result and a stood variant. But as we scan these non-deleted overloads, we notice something interesting. Because I'm trying to maintain that expression equivalence at every level of analysis, I have the appropriate no-accepts here. And those no-accepts reveal to us that to perform these rewrappings, we require move constructibility. But none of these function templates are constrained to require any kind of move constructibility. And so you can, in a Safini sense, form a call to them and then later get a hard compiler error. And the reason for this is because that situation is a problematic one which we have to discriminate and pick out and handle specially. And so now we're going to write a subsumption hierarchy that's going to help us do exactly that. The first concept we defined is called almost wrappable, but remember we defined that C concept earlier, which checks to see if the do_run protocol applies. So we subsume that concept, and then we just layer on top the requirement that we can form some call to wrap with the result of do_run. Note that this may not actually compile because later on you may get a host of errors because you're not passing in things that are appropriately move constructible, but the concept exists and evaluates to true nonetheless. Then we go ahead and we subsume that concept with one which actually layers the real requirement on top. That you not only be able to call wrap with the result of the do_run protocol, but the thing that it returns is move constructible so you can actually perform the remapping. Which gives us all the tools we need to actually implement our customization point object. So let's do that. As I promised you, it's not a function. It's a variable at namespace scope. No ADL need apply here. Which means we're going to implement the behavior by overloading its function call operator. And so let's start doing that. Let's write a function call operator that is constrained on C, that applies whenever the do_run protocol applies, that we're going to use for that happy case when we get back something that is of the form we expect. And sure enough, we're just expression equivalent to do_run. We return it straight through, we materialize no PR values. It's as if the user had just written the appropriate protocol directly in their code. But there are unhappy cases. There are cases where we need to rewrap things, and so we add an overload for that. We add an overload constrained on wrappable, which will kick in when the rewrapping protocol is necessary, would actually compile. And inside of that, we do exactly that. We call the detail function wrap on the result of calling our detail function do_run, and that's that, right? Well, if I left this class exactly like this, then when you call the customization point object with a stream which returns something that can't be rewrapped under our protocol because it misses the requisite move constructibility, you would select the first overload. You would select the first overload and you just return the value of the do_run protocol. You wouldn't move anything, and so there'd be no compiler failure, but what you return wouldn't be of the form the user expects. It wouldn't be a result wrapping a variant. We would be giving them an inconsistent experience, which is exactly what we set out to avoid. And so we need to take advantage of the fact that the subsumption hierarchy we authored on the preceding slide had 3 concepts in it and not just 2. We need to add a deleted member function which activates when something is almost wrappable and is deleted. So in that case, that overload will be selected. The fact that it's ill-formed can be detected at Safini time, and we've actually finally implemented all of the requirements we laid out on the preceding slides in that opaque, difficult to read standardese. But is that all we did? Did we spend the last few minutes just running around impressing ourselves with our ability to read standardese and translate it into template metaprogramming? Or did we actually solve the problem? To determine this, we need to revisit the concrete issue that caused me to go on this journey. And that is a problem of snapshots. A first-class participant in our ecosystem is the ability to ask the system to get you a snapshot of the market data state at an exact instant in time. And we support two ways of talking about time: the receipt timestamp, which is when a packet arrived on our servers, and the exchange timestamp, which is when the exchange tells us they sent it. But there are exchanges that don't work as simply as this. There are exchanges that send you a stream of updates marked with a special indication that those updates are to be considered atomically together. They have the idea of a transaction. And a client wanted us to align their snapshot requests to the last transaction begin, so they would get back bona fide, not intermediate market states. And the problem with this was that fixed cardinality of querying I talked about earlier, of the hierarchy by which we query. Because while I can actually query market data and get snapshots, adding another level in there to pull out the last transaction begin was problematic. I can pull out the last transaction to begin, to be sure. That's just some market data. But if I want to add another layer below it, a layer of market data queries that's predicated on the time that it returns, the rigidity of the previous solution jumps out and bites me. I gave all sorts of bombastic time estimates to the client. I tried to push back on actually implementing this, but all of that was in vain. And so I had to throw away the old ecosystem and design this. And given that I've said I can already formulate a stream or a query that gets me channel metadata, I can get one that gives me symbol metadata, and I said I can get the last transaction begin, I can't just marry it with the snapshot. But I can get snapshots in the old ecosystem. With the new ecosystem, I wrote a new primitive. I wrote a stream wrapper, an algorithm called branch. What a branch does is it wraps a stream and a function. Whenever that inner stream yields a result, it passes it to the function. The function returns a new stream. The stream is added to an internal merge sort state, and then both streams are run together. But each time that primary stream returns a successive result, you call the function again, you add the return stream to the merge sort state, and so your set of queries dynamically expands. At that level of hierarchy, you grow across it. And so now I was able to turn around and say, okay, well, when I query the channel metadata, it's in a branch query now with some function. Every piece of channel metadata I get, I pass to the function and I get back a stream. And that stream is in turn a branch query that wraps a query that gets symbol metadata and branches out by calling a function which returns a stream that gets the last transaction begin. And then when that returns in its own branch, we can finally expand to the last level of hierarchy and get the snapshot at exactly the time we want it. After I reformulated everything in terms of this new framework, went out and did all this generic programming, wrote all these specifications, I was able to sit down and solve that previously unsolvable problem in a week. Not just solve it, test it, deploy it, and get acceptance from the client. And I'd really like to show you the internals of branch, but when I consulted with people who were familiar with the code base when I showed them this talk, they said that I probably wouldn't have time, and I agree. But I do want to show you something in this ecosystem. I want to show you how you can add an algorithm to it, how you can add something that wraps a stream and adds value. So why don't we go back to an old friend, something we talked about earlier. Let's filter. Let's try and write a stream that wraps another stream and just filters results that we're not interested in. But because we actually need to know the type returned by our inner stream in order to mutate it to add the states we need to represent the fact we've removed some results, we need a few more primitives first. We need to be able to actually figure out what the result is that's yielded by a stream. So we write a template type alias that does that. That just computes the type that run returns and uses declval in keeping with our theme to pass through the value category of t. But we know from lengthy explanation earlier that run always returns an outcome result of a stood variant of one or more alternatives. That outcome result layer is invariant. It's not of much interest to our users. We don't want to have to force them to pierce through and get out the type they're interested in every time, and so we write another template type alias that just does that work for them. Armed with this ability to figure out what our interior stream returns, we need some way to take the results the predicate returns false for and remove them for the stream. We need something that changes their category that we call as, which derives from t and changes its category. Note that I'm fully aware of the fact this doesn't play nice with primitive types or types marked final. Rest assured, in our internal code base, as.hpp is substantially more complicated than this. Given that we've written as, we need to specialize our variable template for it to associate it with the correct category, and now we can return our attention to what we actually care about, implementing filter. Figuring out what type it is that filter should return and how we can compute it. And a first stab someone might take is just to define a type trait that does this. Define a primary class template that is declared but not defined, and then use the magic of specialization to pull out that list of alternatives. And then derive from type identity to implement a type trait that just maps through to an outcome result of a variant with all the same alternatives, but then those alternatives, again, all promoted to position. And this seems simple and tempting at first. But let's take a look at a real example. Let's take a look at an example stream. Foo, bar, and baz are just structs, but they all have different categories. Foo is a result, bar is a position, and baz is a completion. Our example stream returns a variant of 4 alternatives. Foo already promoted to position because apparently it's doing some internal filtering of its own and we just want to layer more on top, bar, and baz. Now let's imagine that we go ahead and we instantiate that type trait from the last class, the last slide, with the return result of this stream. We're going to get something that looks like this. Something that is truly and utterly grotesque. Not only does this contain positions and completions promoted to positions, which aren't cases we care about because why would we filter out completions, but it also contains something that is promoted to a position and then promoted to a position again, and perhaps most upsetting of all, it contains a duplicate alternative. I'm well aware of the fact that variant supports that actually, but I have absolutely no desire to interact with that functionality, even if it's been precisely specified and correctly implemented. What we need is a new technique for implementing the return type of filter. What we need is this. And at first glance, this is a terrifying construct. We have a class template that's templated on a category enumerator. And then its sole member is a template type alias, which computes a bool constant which grabs the category of the inner template parameter and compares it to the outer template parameter. And for people who are not comfortable with what this is, immediately knowing the technical name for this class of things might make it even more terrifying because this is a higher order metafunction. But this shouldn't be terrifying because C++ developers since C++11 are comfortable with higher order regular functions. Let's bring ourselves back to regular programming and see if we can make sense of what this is. Category of is no longer a template variable. It's just a function. You call it with a string view and it returns a category. Make matching predicate is no longer a higher order meta function. It's just a regular old higher order function. We call it with a category and it returns to us a new function which captures C, takes in a string view, gets the category of the string view, and just sees if it's equal to C. And then we throw some code in there that actually makes use of this. By sheer coincidence, all of the entries in that vector are just the stringification of the alternatives returned by our example stream. But if we look at this and use some intuition and use the fact that we probably understand higher order regular function and views filter, we can ascertain that this probably just outputs foo. It just extracts from that vector the thing that is a result and discards everything else. And this is exactly what we're trying to accomplish with our higher order meta function. So let's return to that. Let's put that higher order meta function in a detailed namespace and then go off and define what we actually want. A primitive that given a collection of types, a std variant instantiated on those types, will give us back a collection of types that we're interested in, a std variant instantiated on that different set of types. And to do that, we're going to go off and use boost MP11. We're going to use a meta algorithm that takes in our variant and filters it based on the result of some meta function. When we instantiate make matching predicate, when we call that higher order meta function, what it returns to us from that instantiation is a regular meta function. If we feed in the variant of alternatives returned by example, what's going to happen is that mpremoveIf is going to go through each of them. It's going to look at foo. It's going to instantiate the meta function it's given with foo, and it's going to get back a Boolean constant false, which means it remains in the output set. And then it moves on to the next alternative, and it sees that instantiating the meta function for that gives it the Boolean constant true, and so it removes it. And the same for the remaining two alternatives. And so we end up with std variant of foo, which is the only type we're interested in transforming. Because it is the result, it is the bona fide piece of data that example returns. And so when filtering, it's the only thing we need to think about removing from the output stream. And if we understand all of this so far, perhaps the most concerning thing when we zoom in here is the fact that we have to type : template fn because we are in a dependent context. This is something that C++ developers hate so much that get is a free function and not a member of tuple and variant. And the authors of MP11 know this. And so they recognize make matching predicate here as a special construct, something they call a quoted metafunction. And they provide versions of all their algorithms which just accept quoted metafunctions and type out that : template fn internally so you don't have to. So if we just say mp remove if _q, we can get rid of that detritus that everyone hates seeing in their code. We're now one step away from implementing filter, because the last thing that we need is another higher order metafunction. One which, when we invoke, returns to us a metafunction which wraps the result, which wraps the thing it in turn is invoked with in an as that just promotes that thing to the category the higher order metafunction was invoked with. Now we can turn around and we can actually use all of these things to implement filter. A binary class template which accepts the inner stream it wraps and the predicate, and dutifully has both of them as member variables. Then we start on our metaprogramming adventure. We go and we get the run result value type, so the inner variant, not the outer outcome result, that we obtain when we invoke inner as an L value. Once again, we're careful to communicate the value categories through this ecosystem. For our example, this just gets a stood variant of foo, as, position foo, bar, and baz. And while we're interested in passing through all of those types, because we're interested in being able to pass through everything that our example stream returns untouched, we're also interested in looking at just the results. And so we go off and we use that primitive we just wrote to extract those. We say, hey, can you give me back a variant that just contains the result of this variant? And so what we get back is stood variant of foo. But now we need to perform an additional transformation, because the whole point of the predicate returning false is that we remove that result from the output stream but still yield back that result as a position. So it's not considered part of the bona fide output stream. So we need to use another meta algorithm. We need to use mp transform q and give it the result of invoking our higher order metafunction with category position, which returns to us a metafunction which, when instantiated, just transforms the type it's instantiated on to wrap it in as and make it a position. And so we transform each element of the variant that gives the inner results type by promoting them to a position, which gives us back a variant that's stood variant of as position foo, which is exactly what we want to add to the output set. It's what we get when we promote the result to a position because the predicate returned false. So now we have two different sets of types, two different variants we're interested in, and we're interested in yielding the union of the two. And so in order to form our final result type, we need to use two additional meta algorithms. We need to append the two sets together, and then we need to deduplicate them to avoid the possibility that we'll end up with a variant that contains duplicate alternatives. Question?
So in this case, won't the specific conditions of the original filter and the transform prevent duplicates? Because
so what happens is when we filter the variant down, we get one that just contains a result. And then we transform it and we promote it. And if we union it back with what's example returns, we'll have that promoted one twice because there's no deduplication. Because append just concatenates them together. Right? So that inner append there just concatenates the two sets together. So in our example, we'd end up with stood variant of foo, promoted foo, bar baz, promoted foo. So we deduplicate by removing the last one. So we don't end up with a duplicate alternative. Did that answer the question?
Yeah, I just got a little bit confused about how the things mapped onto the categories.
No, I mean that's fine. This is not trivial code to understand. So now that we're done with our adventure in metaprogramming, we can go and use this type and actually implement filter. We can go ahead and we can write some real code. The first thing we do in run for filter is, of course, run the inner stream, because without knowing what it returned, we can't do anything. This outcome try macro provided by the outcome library just transparently returns a failure if whatever you pass on the right-hand side fails. Otherwise, it extracts the value and binds it to the declaration on the left. So auto res in the successful case refers to a variant, and in the unsuccessful case, it refers to nothing because we already returned. Now we need to do something that most C++ developers don't like to do. We need to visit a variant. And people don't like doing this because we don't have pattern matching in the language. One thing I see people do in this case is write a fully generic lambda and just use an if context per cascade. And I don't really like that technique because while we don't have pattern matching, we have something that at least is kind of like pattern matching. We have overload sets. But unfortunately, we don't have a primitive in the standard that allows us to compose callables together into an overload set. So I just went out and ad hoc wrote one myself. I just derive from all of the callables, construct all of them in my constructor, and pull all their function call operators into the overload set that I'm synthesizing. I'm well aware of the fact that this doesn't work for function pointers. It just so happens that I don't actually care about function pointers. Of course, because no one wants to type the name of lambdas, we give this a deduction guide. Then we can just go back and plug it in as our visitor and start putting in lambdas to actually implement our functionality. The first one is completely unconstrained and will be invoked for every position and completion and just maps it through. Because positions have already been removed from the bona fide output stream, and if the thing is complete, we're never going to filter that out. We're just going to return it, and we'll never get called again. Which leaves us using the concepts we defined earlier to constrain another addition to our overload set. One which is constrained on a result, which is something we're actually interested in processing and layering some logic on top of. In this case, we need to, of course, ask the predicate whether we should filter the thing out or leave it in, and so we go off and we invoke the predicate. Note that I don't do the normal standard C++ thing of saying, well, you have to be really nice and not mutate the thing I provide you, otherwise it's undefined behavior. I just use the type system to model that. I just promote the result to const and pass it in and use the type system to prevent the compilation of ill-defined predicates that would try and mutate it. In the case where true is returned, I just do what the unconstrained lambda does. I just return it untouched because that's exactly what filter does for things that qualify for inclusion in the bona fide output set. On the other hand, if the predicate returns false, I need to go off and do some lifting to actually wrap that in an as position, to change its category so that control will be returned to the caller to be nice in yielding the CPU, but they won't be deceived into including this in the output set they actually send to the user. So now I just need to write some constructors for this class, or rather just one constructor, a constructor that takes the inner stream and the predicate. I use the template for the first parameter because I want to reduce the number of moves involved here. I don't want people moving into my constructor and then me moving from the constructor into the data member. They can just move transparently through and I forward. Now, because I've done this, because I've elected to use this technique, what I've done is I have decoupled the first parameter to the constructor from the first argument to the class template. And so I need to turn around and write a deduction guide to restore C++ 17 class template argument deduction functionality. But we're writing a generic library. We're trying to be as permissive as possible to the types our users try and integrate with us. And types can be immovable. What if our user has a stream that's immovable and they want to put it in our type? Well, if we go back and we look at the constructor, we have a forwarding reference. We don't constrain it to be related to inner, so if the user passes one argument that can be used to construct an inner, we'll just construct it in situ. There's no problem. There will be no move. The object will just spring into being inside of my object. This technique has been in use all the way back to C++ 98. But the C++ type system is rich. There are types in the type system which aren't unary constructible. What happens if I want to construct something with a different arity? And this is no longer a hypothetical problem because I actually have a type like that in my ecosystem. The glue that goes between this new ecosystem and the old ecosystem that wraps the thing that we were calling a query in the early part of the talk. And the reason it's immovable is because unbeknownst to you, I didn't litter my slides with it, OpenQuery actually has a bunch of member functions that are expensive to call, like one that actually synthesizes the current canonical path to the file the update came from. I don't want to have to eagerly call those and put them in a struct just to return them for my new ecosystem, so that struct I return has a back reference to the query so you can go and lazily call those if you want to. But that means that I need reference stability. I don't want the stream to be accidentally moved, and so I just go ahead and make it immovable. But if we think back in time, OpenQuery is not unary constructible, it's trinary constructible. I want to be able to write code that looks like this. And at this point, everyone's probably thinking, well, why don't you just reverse the order of the constructor parameters and make the trailing one a pack, and then you can in-place construct the stream inside of yourself. And that was a great solution in C++ 11 because in-placement construction was the basis operation for deferring responsibility for constructing objects contained by something. But we're well past C++ 11 now. We have C++ 17. I'm not concerned with types that are trinary constructible. I'm concerned with types that are immovable and are returned from functions using C++17 guaranteed RVO. I want to be able to write a function like this that returns my immovable stream and then integrate it with my ecosystem like this. But as soon as I write this, I'm going to materialize the PR value returned by create query, bind it to a reference, and then it has storage. And in order to get it into my class, I need to move it. But the whole reason we're looking at these slides is because I said the thing is immovable. And none of this would be a problem if C++ would just go ahead and have lazy function parameters, but it doesn't, so we need a workaround. We need something that can materialize a PR value directly into storage and still satisfy the constraint stood constructible from. And if you think about this long and hard, or just go talk to David Stone at a conference like I did, you'll realize that you need the implicit conversion operator. You can go and write something like this with a convenience class that implicitly converts the query of OpenQuery and just internally calls the function, and then the code at the bottom actually compiles and runs. But this pattern is full of boilerplate. It's not very reusable. Not only have I written something that solves this internally, but recently on the reflector, I've seen a proposal to add it to the standard library. Something that looks like this, which wraps a function whose constructor just takes it and stores it internally, and which uses C++23 deducing this to be implicitly convertible to whatever the wrapped function returns, given its nullery invoked with the value category of the class that contains it. The way we accomplish this is we're templated on ourself. We now receive ourself as a bona fide argument, and so we can forward ourself before accessing a member, which promotes it to the same value category of us, and then we unary invoke it. That declaval after operator is just me putting that type into the declaration of my function. Armed with this, we can go back, and the code gets a lot more terse. And if you're willing to go off into the forbidden land of macros, you can make it even more terse still. But in trying as hard as I can to support C++17 guaranteed RVO, I've gone off and I've forgotten about another C++17 feature, one which I was integrating with earlier in this talk. I've forgotten about class template argument deduction because I'm explicitly listing all of the template parameters to filter. What I actually want to write is something like this, but if I do, filter is going to deduce that its stream parameter is an elide of some lambda, which isn't a stream, and I'm going to end up with horrific compiler errors. So I want to introduce you to one last primitive I have in the library, something that I call deduce, which in its unspecialized form is just an alias for std remove cvref. Then we're going to open a detail namespace and add some machinery. We're going to add a primary class template that's declared but not defined, and we're going to specialize it for the special case when it's instantiated with an elide of t. And all we're going to do is we're going to pull that t out and make it available via this detail type trait. Then we can go ahead and we can specialize deduce. We can specialize it constrained on the validity of the extract type trait. So if we actually get in an elide with some cvref qualification, this specialization activates. And this specialization doesn't compute std remove cvref of t. It goes off and it computes whatever it is the function wrapped by elide would return if we use C++23 forward like to apply the value category from the elide on to the function. If that sounds complicated, I invite anyone to raise their hands right now and ask about it. Marshall.
No, I'm not going to ask about it. I just think it sounds complicated.
Okay. So Marshall agrees. This is complicated. Let the record show.
Instead of doing this, would it have been possible to write another class template argument deduction guide? Like on your, I can't remember what
You're skipping ahead.
Yeah, you're skipping ahead. That's what we're going to do. Yeah. The first, I need to go ahead and acknowledge the fact that we don't write type traits anymore because we're in C++11, and I need to add a template type alias. And then I need to look behind the fold and say, we're just going to rewrite our deduction guide so it now accepts a forwarding reference. And instead of mapping through just inner and predicate, it filters inner through deduce of t, which means that if I'm trying to deduce the class template arguments from a call from a stream, right, you're not going to get the specialization on the preceding slide. It's just going to be like the old deduction guide. It's going to do remove cvref of t, and you're going to get a template of the stream you're actually providing and the predicate. But if you provide an elide, the special functionality of deduce kicks in. It strips off the elide and gets the type it actually converts to with that value category, which is why I had to convert the first argument to a forwarding reference, and then it plugs that into the class template instead. So now what I wrote on one of the preceding slides that I said wouldn't work because we would deduce allied, instead deduces whatever it is that allied converts to. And so what I've accomplished here is I provided a generic building block, filter. I've not only provided a generic building block, I've shown you how it composes with other streams, and you can open up your imagination to see how that would compose with other algorithms you could write, like branch. But then, as the icing on the cake, as the last step, I've shown how we can actually construct immense graphs of these compositions directly in place with no intermediate copies or moves, knowing exactly how big they need to be, exactly how much storage needs to be allocated with no dynamic allocation behind the scenes. And I could go on about this ecosystem for quite some time, as evidenced by the fact that I didn't feel like I had time to cover branch. But CppNow talks are of a finite length, and so I want to leave you with a few parting thoughts. The first one is the fundament of generic programming in C++, and that is to think in terms of operations, not types. You're not concerned with the exact type A, you're concerned about what you want to do with every type in your ecosystem, which lends itself to asking yourself what you're doing generally, not particularly. You may be writing two classes because they need to interact with each other, but that particularized interaction isn't what's meaningful when you're trying to build a large framework, when you're trying to build a generic library, when you're trying to compose a large software system. You need to figure out what you're actually doing in the Platonic domain and how you can model that in your actual code. But in the process of figuring that out, you don't need to be afraid to learn about the problem domain as you go. Start with something low level and ugly like OpenQuery and work your way through the problem domain, learning about every sharp edge therein. And then once you feel like the code you've written is going to collapse under its own weight, when you've learned valuable lessons, you need to out yourself as a software engineer and not a coder. You need to realize that all the code you've been writing is just a means to an end. And the end was what you learned along the way. Now you need to take that knowledge, figure out how it generalizes your problem domain, and write code that actually addresses the core issue that you're going to be happy to work with as you iterate into the future. Other questions? Question.
You mentioned, I think, lazy function parameters, and I was wondering if there's other features, either forthcoming or not yet proposed, that you would look forward to do this maybe a little bit more simply, a little bit less intimidatingly.
I guess so allied is actually, there's a paper in flight. It doesn't have a P number. It's not been published. Yeah. That's the reason why I took the screenshot off the slide. And so, that would help reduce the boilerplate of having to write my own allied, but the call site would still kind of look ugly. I think that that lazily evaluated parameters are what I actually want for this. I know that people feel like there's a lot of sharp edges with the syntax, right? Because it does all sorts of things like breaking the function call boundary and how you materialize references and stuff like that. But I think that given that we added guaranteed RVO to the language in C++17 and working with it in a useful way is as indirect and complicated as is on these slides, that's the reason why I want lazy function parameters. The fact that I can actually properly overload like and or with it is just the icing on the cake for me.
Cool.
Gashper.
So I think what you also need out of the papers is 2830, which is context per type ordering. You need 2825, which is expression aliases, which is the first half of what the second half gives you. You need Decoupling, which is the oracle for overload resolution. And those two together give you expression equivalent without messing with overload sets.
So basically what I need to make this better is all of Gashper's papers to sail through and be adopted.
There's a reason I proposed them, and it's this.
Yeah, I agree that the type ordering thing would get me quite a bit. The only reason why I'm not really upset I don't have type ordering is because the way that composition works in the streams, you end up at each level, and at the compile time at least, tearing variants apart and putting them back together. And so the fact that at two levels of analysis, the variants might have the same types in different orders. It might stamp out a few instantiations, but it doesn't lead to problems like what you were talking about in your talk, where you have like a basis operation that thinks two things that are the same are totally different, right? Because the deconstruction and reconstruction of the variant at every step kind of solves that for you. All the primitives that I have that merge heterogeneous streams together, there's one I have that's actually just called variant and is internally a variant of streams, just synthesizes its own variant, and then at successive layers we resynthesize a different one. It would be really nice for them all to be canonical. I'd be very, very happy about that, but it hasn't broken anything yet. right? Maybe I'll come back next year and give an entire talk about how not having type ordering broke my streams framework, and I need you to adopt Gashford's paper today. Are there any more questions? If not, there's 15 minutes left in the slot, and I prepared a list of suggested questions if you want to ask any of them. If everyone's satisfied with the answers to even these questions, then I'll call it a day, and thank you very much for attending.
Oh, I mean, how are the compile times?
So what the interesting thing about this actually is the compile times, what I had before was a fixed cardinality hierarchy framework that was still generic. And so it had compile times that were like most generic code. And so when I put this in, the compile time actually didn't change that much. The weirdest thing that I've taken away from this that I haven't bothered to diagnose because I'm too busy and I don't understand the involved components enough is that when I compile very complicated DAGs with this framework and I enable address sanitizer, the compile times are insane. We're talking like maybe 45 seconds, but then the assembler runs for 40 minutes. And I have no idea why. If I turn address sanitizer off and build in debug mode, it assembles almost instantly. I have no idea why. It must trigger some degenerate behavior inside the assembler, which I just don't have time to diagnose.
The inliner, I have run into this.
Is the inliner combined with address sanitizer?
Yeah, because address sanitizer instruments a whole bunch of basic operations, and so the inliner has to work super hard to prove that things are the same.
That was my completely ignorant outsider's impression was, oh, it's inline that's doing this to me. And so now I have someone confirming that it's inlining doing it to me.
You can do f-profile trace and you'll see it.
Oh, you mean like with Clang?
Yeah.
Yeah, the only problem with that is that at some point we broke our Clang build and we don't release on Clang, and I haven't fixed it yet.
Just do it with GCC, it has it.
Oh, does it? I went to a talk a while ago where they said it was just Clang that had it. So.
No, GCC has its own. The output is different. You need to understand very well what the individual passes are doing. You don't get timings for individual template instantiations like you'd get with template in Clang, but it's serviceable.
Well, I'll have to go and use that then, because I'm really interested to know like where the pain points are, because I haven't even attempted to optimize the compile times of this framework. I wrote tests for it, implemented the specification, it worked, the code built, I shipped it to a client, and I didn't really have time to go back and revisit the fact that maybe I can implement run slightly differently and it compiles 3 times faster. So, Ben.
All right, so this wasn't reinventing coroutines, but do you have any interest in using this with coroutines?
So I do have interest in people who are consuming it electing to use coroutines on the outside. This looks a lot like coroutines, but the reason why I don't think it was reinventing coroutines is because the best thing that I get out of this ecosystem, I didn't have time to show, and that's that run is not the only CPO that we have in this ecosystem. We have 3 CPOs. One of them is run, and one of them is called source. When you call source on a stream, if the stream doesn't implement the protocol, it falls back and returns you that stream itself. And what that's communicating to you is you're asking the stream, who made you generate the last thing you returned to me, right? When you failed, why, right? The result, where did it come from, right? And so if you actually implement the protocol, you can return either the reference to a different stream or a variant of pointers if you wrap different types. And what that lets me implement is an algorithm, a generic algorithm I call backtrace, which when there's an error that comes out of the top of the stream, I call backtrace, and it goes all the way to the bottom and then walks up and hands me back each of the streams involved in that. And it's not like a stack trace, you never lose frames because inlining is on a separate way through. And so then you can use the 3rd CPO, which is describe on each stream, and that lets each stream output a textual representation of its internal state. And so you get like an immense amount of context, which comes in handy because the user will submit one query, be like, it didn't work. And if I go to the log and it just says file not found, that doesn't really help me. So instead it just outputs pages of descriptions of exactly which path it took to the DAG and what happened at each level and what the state of each level was. And so with coroutines, I wouldn't be able to get that. But other than that, I think this is kind of isomorphic to coroutines. I just couldn't get that. But I do think there's an opportunity for you to have a stream that wraps a coroutine and to have a coroutine wrapper that wraps streams on the outside. And then internally it could do backtrace, at that boundary. That's one thing we do when we type erase this stuff, right? Because we type erase it, you can't call source anymore. Internally, it needs to provide some primitive that gives you back the description already rendered in some way. Kirk.
So in a closed source implementation, Lewis Baker has implemented backtraces for coroutine stacks. And it was very, very useful, but it's something that changes the task type. And so when defining the task type, one of the things that needs to be decided is whether or not we're going to add the functionality to be able to explore and record.
Does that come at an overhead with respect to like the ability to inline and optimize around coroutines? Because one of the reasons I find this attractive is because they're separate paths through the backtrace.
No.
No, it doesn't. Okay. Does it require compiler magic?
Lewis will have the better answer.
Okay.
My understanding was that it was going to be better with compiler magic.
Okay, yeah, I'd be interested in like looking at coroutines again if I had access to something like that, because the error reporting was one of the fundamental drivers, even though it's not on these slides, because one of the reasons I realized the old hierarchy mechanism lacked context is because if the precursor queries failed, like I said, you need to get channel metadata, symbol metadata, and then market data. The market data queries failed, I got a good error message, but because of the way everything was structured, if you couldn't get something out of the symbol file, it just blew up and said like, file not found. And that's not helpful to me at all. When I get error reports like that, I just lose my mind. So yeah. Any further questions or should we call it there? Well, thank you all for coming.